Welcome to Lecture 41, the first of 3 lectures on optics. Now, we've just come through a long sequence of lectures on electromagnetism, culminating in Lecture 40 in our understanding that Maxwell's equations lead to electromagnetic waves and that we can identify light as an electromagnetic wave. So in principle, everything I'm going to say about optics in the next 3 lectures can in fact be derived rigorously from Maxwell's equations. That would be difficult to do. I'm going to refer to Maxwell's equations occasionally. Most of the time, we can ignore the fact that light is an electromagnetic wave. In fact, we can ignore the fact that it's a wave at all. Because whenever light or any other wave interacts with a system that is large compared to the wavelength, we don't notice the wave aspect of that thing, light, sound, whatever it is. So when light is interacting with objects that are large compared with the rather tiny wavelength of light, we can ignore the fact that light consists of waves, and we can consider it to consist of rays, straight lines of light that move straight until they encounter some other medium, and then they may bend or they may reflect. They may reflect or they may refract, or the physics words we use, and then they travel in straight lines, again called rays, within those new media they have come into. So we're going to use what's called the ray approximation. And again, it's good when the size of the systems we're dealing with is much larger than the wavelengths. By the way, ray optics is also called geometrical optics because of these straight line rays that we're drawing. The simplest phenomena we'll deal with geometrical optics or ray optics is the phenomenon of reflection. And before I talk about reflection and give you some examples of it, let me just mention here's one place where we do connect to Maxwell's equations quite readily, because what makes something a good reflector? Well, if you think about things that are shiny, they tend to be metals. A piece of aluminum foil, the aluminum coating on the back of a mirror, just a shiny piece of copper. Why are those things good reflectors? They're good reflectors because they're metals, and that means they contain free electrons. And light is an electromagnetic wave, even though we're not going to need to know that for most of these optics lectures. And so in comes an electromagnetic wave with its electric field. The electric charge of the electron responds to that electric field. The electron oscillates at the frequency of that incoming wave, and oscillating or accelerated electric charge is the source of electromagnetic radiation, and the free electrons re-radiate that wave, and out it goes. And that's a very microscopic electromagnetic description of the process of reflection. So metals tend to be good reflectors. Let's look at a couple of reflectors. Over here, I've got a nice white board. It's white, meaning it reflects all light incident on it. It is basically reflecting 100% of the light that lands on it, approximately. And over here, I have a mirror, and regular ordinary home mirror, and the mirror is also reflecting all the light or almost all the light that falls on it. What's the difference between the mirror and the whiteboard? Well, the difference actually has to do with how smooth their surfaces are. They both are reflecting, and they're both reflecting in essentially the same way, obeying what we call the law of reflection. So let's take a look at the law of reflection. In the law of reflection, we have an incident ray coming in. Here's our ray approximation. It makes some angle, theta 1, with the normal, that is the perpendicular to the system that it's hitting, to the medium that it's going to reflect off of. And the rule for the reflected ray, and we could prove this rigorously with Maxwell's equations, is that the reflected ray goes out at the same angle relative to that perpendicular, the dashed line in this diagram, that it came in at. That's the law of reflection. The angles of incidence and reflection are equal. By the way, that term angle of incidence is going to apply when we look at the next phenomenon also, refraction. So what's the difference between my whiteboard and my mirror? Well, the whiteboard and the mirror have different surface roughnesses. The mirror is very smooth. It's got to be quite smooth. It's got to be so smooth it doesn't vary a whole lot compared to the wavelength of light, at least over small regions of its surface. So it's very smooth, and it exhibits what's called specular reflection. All the light rays hitting it coming in at a given angle hit the mirror at that same angle, and they bounce off at the same angle, and that's why we get a nice, shiny mirror that gives us an actual image, and we'll see in a moment how that image comes about. The whiteboard is similar, except its surface is rougher. The incoming rays still obey the law of reflection. But in this picture, this microscopic picture of it, because the surface is rough, there are all kinds of different angles. So light rays that are coming in all at the same angle are bounced back at all kinds of different angles. We can't form an image that way, and we get this sort of incoherent mess of light rays coming out in all directions, and therefore the whiteboard looks white pretty much no matter how you look at it. So that's reflection. The law of reflection is simply the law that says the incident ray and the reflected ray come in and out at the same angle, and it happens both in the mirror and in the whiteboard. It's just the whiteboard, those angles of incidence relative to the normal to the surface vary because the surface is rough. So that's reflection. So let's take a look at our mirror over here. I look in the mirror, I see myself. I see things in the studio that you don't normally see behind us. There I am in the mirror. Where am I exactly? And here's my left hand waving at the mirror, but in the mirror it looks like my right hand. How is all that happening? So let's take a look at how a plane mirror like that, a flat mirror, forms images. In the next lecture we'll look at curved mirrors, which are more interesting. But a flat mirror is interesting in itself. So let's see how this flat mirror forms images. So here's a diagram that shows a mirror running vertically down the middle, and we'll have some object. In this case, it's a little triangle, and you can actually think of that as the head of an arrow. I'll be using arrows for objects in optical diagrams a lot because they're distinguishable one end from the other, and yet they're very simple objects. So here's what happens. Light from the object shines toward the mirror, and you can see in this case 3 light rays going out. They bounce off, obeying the law of reflection. And they continue to diverge as they were doing coming from the object. And down at the lower left, I've shown an eye, which is looking in to see the image of that object in the mirror. Now, the solid lines I've drawn here, which are all to the left of the mirror, show the actual paths of the light. But to that eye, it looks like that light is diverging from a point behind the mirror, as far behind the mirror as the actual object is in front. And I've marked that with dashed lines which show apparent light paths. There is nothing behind the mirror that we're seeing. And yet it looks like the image is behind the mirror. For that reason, because the image isn't really there, because there isn't really light coming from the image, that's called a virtual image. And we'll use that term over and over again when we look at more complicated images formed by lenses and curved mirrors. A virtual image is an image that isn't, in some sense, really there, in the sense that light is not actually coming from the place where the image is. It's going to be the same size as the object. And you can see in this diagram that the image in the plane mirror is going to be the same distance behind the mirror as the object is in front, and it is actually reversed. And you might think it's reversed left-right, sort of, but what it's really reversed is front to back, because the part of the object facing the mirror of the actual object corresponds to the part of the image facing the mirror, and those directions are reversed. That is what causes my left and right hand to appear reversed in the mirror, but it's more correct to say that the mirror reverses objects front to back than to say it reverses them left to right. Okay, let's take a little look at how we might use plane mirrors for something more interesting than just preening our faces in them. Here's a device called a corner reflector. A corner reflector consists of 2 mirrors at right angles. In 3 dimensions, it's called a corner cube, and it consists of a 3rd mirror at right angles to those 2. And the corner reflector or corner cube has the wonderful property that when light comes in and reflects off one mirror, hits the other mirror, and reflects back, it comes back exactly parallel to how it came in, regardless of what that incoming angle was. So here's a light ray coming in, reflecting off the 2 mirrors, and coming out not in exactly the same place, but parallel to the direction it came in on. Go to some different light rays, and the same thing happens. Let's do a quick demonstration of that with our optics setup we'll have over here. Okay, so what we have here, which we'll be using in this lecture and the next, is a whiteboard. It's a magnetic whiteboard, and I have a number of optical components I can put on the board, and they'll stick there because they got magnets on the back. So here, for example, is a little simple laser, which, if I turn it on, will shine a beam that we can see against the board, and we can put optical components, lenses, mirrors, whatever, on the board and see how those light rays behave. So let me take a couple of simple mirrors. They're just blocks of glass with a shiny mirror piece, and let me put them at right angles, because that's what makes a corner reflector, as I just showed. So I'm going to put 2 of them together at right angles, and I'm going to shine a beam of light in, and you can see that the beam comes out. It's going in at that angle. It comes back out at that same angle. If I rotate the laser beam, it still comes out at the same angle it went in at. I can put it in anywhere, and as long as it hits at such an angle that it's going to intersect both mirrors, it will come back out at the same angle it came in with. This is actually a very useful thing. A lot of laser experiments that involve sending a laser beam some distance and hoping it will come back involve such a system because you don't need to align the reflector perfectly. When astronauts first went to the moon, they actually took three-dimensional corner reflectors to the moon, and they were used for laser ranging experiments. Laser beams were aimed at those corner reflectors, and they had to hit them, but they didn't have to hit at any particular angle because the reflector returned the ray in the same direction it came from. And those were used to determine the distance to the moon to within a matter of inches. By the way, those helped confirm Einstein's general theory of relativity. So there is a practical example of what we can do with reflection in plane mirrors. Now, while I'm here at the optics setup, I'd like to move on to a second phenomenon, and that's the phenomenon of refraction. That's the bending of light as it passes from one medium, transparent medium, into another. So to do a demonstration of refraction, I'm going to take this semicircular piece of glass. Now, this is glass that has no reflective surfaces or anything on it. And I'm going to use my laser. And I'm going to shine the laser right into the box. And you can see into the glass. And you can see when the laser beam is going in right perpendicular to the interface, to the surface of the glass, it just goes straight in and comes out the other side. I'm using the curved piece because I want to ignore what's happening at the far end, and that will be a little easier to understand. But notice what happens if I make the ray come in to the glass at an angle. Well, now you see that the ray is coming in, and it's going at a slightly different angle. It's being bent. If you look carefully, by the way, you may see a slight hint here of a reflection, because whenever light hits an interface between two media, it doesn't only refract, it also reflects. And that's, by the way, true for any wave when it goes into a different medium. That's how, for example, medical ultrasound works, by reflections off different materials within the body. As I make that angle of incidence steeper and steeper, further away from that perpendicular, you can see the bending becomes more pronounced and more dramatic. That's the phenomenon of refraction. And we want to spend the next few minutes looking at exactly why refraction occurs, and we want to understand the law that governs refraction. So I'll turn this off, and we'll take a look at why it is that refraction occurs. So here's a wave picture. We're going to take a little bit of a wave picture here, and here's the deal. Different media have different speeds for light or any other wave. So, for example, light moves more slowly in glass than it does in vacuum. It moves, in fact, at about 2/3 the speed it does in vacuum. And we define the index of refraction of a material to be the ratio of the speed of light to the speed in that material. So, for example, in glass, the index of refraction is about 1.5. That means the speed of light in glass is c divided by 1.5. The index of refraction in water is about 1.3. So light moves a little faster in water than it does in glass. The index of refraction of diamond is 2.4, one of the highest indices of refraction of ordinary materials. And that's part of what gives a diamond gemstone its quality, its sparkling quality. It isn't just that it's a shiny piece of stuff, it's that it has a very high index of refraction, and there's a lot of bending of light going on in there. So in this picture, I'm showing medium 1 in the upper region. There's an interface between two different media. Medium 2 down below. You could think of medium 1 as air and medium 2 as glass, as in the demonstration I just did. And here come some wave crests moving in medium 1 with some speed v1, which is c, which is such that n1 is c over v1. That's the definition of the index of refraction. And then they move more slowly in medium 2. And because they move more slowly, you can see that they're slowing down. Because of that slower motion, in order to keep the frequency of the waves the same, which it has to be, the same number of wave crests have to cross that interface coming in as going out, the waves have to slow down because the speed is less, and consequently they bend as shown. And what we're interested in figuring out here is the angle θ1 and the angle θ2 and how those two angles are related. So that's a wave picture of why refraction occurs. And to figure out exactly what's going on here, we're going to go to our big screen and look at the relationship between those two angles, the angle of incidence and the angle of refraction. So let's go there. So here's basically the same picture we were just looking at. And I'm going to derive what's called Snell's law. And if you ever took physics before, you saw Snell's law, somebody told you Snell's law is how refraction works. We're going to derive Snell's law and see how refraction works. So here come the wave crests heading in. Here is that normal to the interface. Here's medium 1. Here's medium 2. Here are rays representing the incident light, rays representing the refracted light. Theta 1 is the angle of incidence. Theta 2 is the angle of refraction. We want to know how they're related. Wave speed, always for waves, v, the speed of a wave, is the frequency times the wavelength. Now, as I indicated, the frequency can never change because the same number of waves, if you sit on the interface, you'll see so many wave crests coming in every second, and you'll see so many wave crests going out, and those numbers have to be the same because waves aren't disappearing at that interface. These are transparent media. They're letting all the wave energy in. So the frequency stays the same. What that implies is that the wavelength in medium 2, down here, is shorter than the wavelength in medium 1 because the speed is f lambda. F is the same in both cases. The speed is lower in medium 2, so lambda has to be lower in medium 2 by that same factor. Now let's look at a couple of triangles I've marked here. Triangles with angle theta 1 here and with angle theta 2 here. Notice that those triangles are right triangles because this side is perpendicular to the wave crests in each of the two different media. So they're both right triangles. And second, they share a common hypotenuse. And that's what's going to enable us to figure out what's going on here. They share that common hypotenuse. And remember that the sine of an angle is the opposite side over the hypotenuse. Well, look up here. Here's the opposite side for this blue shaded triangle. That's the opposite side, opposite theta 1. And so by definition, the sine of angle theta 1 is this distance, which, lo and behold, is the distance between wave crests. That's the wavelength, lambda 1 in medium 1, divided by the hypotenuse. And similarly for this orange triangle, here's the opposite, and that is the wavelength, the distance between wave crests in medium 2, divided by that common hypotenuse. So the triangles share a common hypotenuse, so that hypotenuse can be written as either lambda 1 over sine theta 1 or lambda 2 over sine theta 2. And we're going to not worry about the fact that it's a hypotenuse anymore. It's given us this wonderful equality because, in fact, those two triangles have the same hypotenuse. So let's take what we've just found, that lambda 1 over sine theta 1 is equal to lambda 2 over sine theta 2. And let's work with that a little bit. First of all, let's look at the wave speeds again. V is f lambda, always for a wave, so lambda is v over f. I didn't write that explicitly before, but that's what tells us immediately that the wavelength is proportional to the wave speed. The wavelength is smaller in medium 2, where the wave speed is lower. I can just take this relationship and take the reciprocal of both sides. It's still a perfectly valid equation, so let me do that. Now, the refractive index is defined such that the velocity is c over n. The velocity of a wave in a medium, a light wave, in a medium where the index of refraction is n, is c divided by n. And n is bigger than 1, so the velocity is smaller than the velocity of light in vacuum. So there's the relationship between the speed and c and the refractive index. And that implies that lambda, which is v over f, becomes c over n times f. Because lambda is v over f, v is c over n, divide that by f, we've got the wavelength in either medium. Different in the two media because n is different. So now I can write the wavelengths, which I had on the bottom. They were downstairs here in the denominator, and so I'm going to write nf over c, where I see 1 over a wavelength. So n1 f over c sine theta 1 equals n2 f over c sine theta 2. And common to both these are c and f, because again, the frequency doesn't change. The wavelength does, but the frequency doesn't. So that's in common, and consequently, we have Snell's law, n1 sine theta 1 equals n2 sine theta 2. And anyone who's taken any physics has seen that. There's where it comes from in the approximation of ray optics. And again, we could derive it right from Maxwell's equations, but this is a simple but perfectly rigorous derivation of that result. So we've got Snell's law. We understand how refraction occurs in the wave picture. Let me give you a couple of examples. Here's a common thing you deal with probably every day, a CD or a DVD or a Blu-ray disc. These discs contain enormous amounts of information. A Blu-ray disc contains 25 gigabytes of data because it's packed into very, very tiny structures on that disc. How can we possibly make that work when a dust mote would be big enough to wipe out thousands or even millions of bits of data? Well, the answer involves refraction. Here is a picture for an old-fashioned sound CD and audio CD, but the picture would be similar for a DVD or Blu-ray disc. And you see an incident laser beam, the laser that reads the information off the disc, is coming in at some angle, and there is a refraction occurring at the interface with the plastic of the disc. And one thing that does have to be pretty standard in discs is the index of refraction of that plastic. It's standardized at 1.55, and that takes the incoming laser beam and takes it to a very carefully focused, very tiny spot on the laser itself. And that spot is tinier than any dust mote, but where it entered the plastic, it was much bigger. And that's the reason CDs are basically clean. It takes a lot of dirt and dust to make them not work. So there is one example where we use refraction, straight line refraction, not refraction in lenses yet. We'll do that in the next lecture, and it becomes of practical significance. Okay, let's look at another phenomenon that occurs associated with refraction, but also gives us back reflection. So I'm going to go over to my experiment here, and I'm going to set it up again for a different experiment. Here I've got the same piece of semicircular glass I used before, but I now have the curved edge facing my laser. And you'll notice the laser beam is entering the glass, going straight in. Angle of incidence is 0. Angle of refraction is 0, goes straight through and comes out. Now watch what happens if I come in at different orientations. I'm coming in normal, perpendicular to the curved part. That's why I'm using this curved piece of glass. Let's look at what happens at this other interface between glass and air. Going from a medium with higher refractive index to one of lower refractive index, the light bends away from the normal. It bent toward the normal when we came in. When we go out, it bends away from the normal. And now watch what happens as I increase that angle. Here I am at about 30 degrees, and we're going out at about 40-something degrees. And here I am at 35 degrees, and we're going out even steeper. And here I am at 40 degrees, and wow, we're going out really steeply. What's going to happen? Well, there's going to come some angle, and it's coming up pretty soon here, where that outgoing light ray just barely skims along the surface. And after that, it basically has no place to go. And so look what it does instead. It reflects. It reflects off that interface between the transparent glass and the transparent air. There's no reflective substance there, and yet we get almost perfect reflection. That almost perfect reflection is called total internal reflection. It occurs when light is trying to go from a medium which has a higher index of refraction to one with a lower index of refraction, and if the angle is above some critical angle, the angle of refraction in the lesser index medium, in the air in this case, would try to be greater than 90 degrees, and that can't happen, and so it reflects totally instead of refracting. So we get reflection out of refraction with this particular setup. Let's go to our big screen and see exactly how that happens and what that critical angle is. Okay, so let's take a look at this phenomenon of total internal reflection. We're going to base it on Snell's law, which we just worked out for ourselves, so we understand where that comes from. And what we have here is some kind of medium like glass. It's the first medium, the medium in which the light is going to originate. In fact, I've put a light source down there in the corner. And I'm going to ask what happens as the light from that light source hits this interface at different angles. So here is a relatively steep angle. I'll call that ray number 1. And ray number 1 is going to refract a little ways away from that normal, but not a whole lot. If it had hit head on, it would have gone straight through. Here's ray number 2. Ray number 2 is at a bigger angle relative to the normal, and so it refracts more. And here is that special ray, ray 3, which just skims along the surface. Now notice, for ray 3, the angle of refraction is 90 degrees. If I send out a ray at an even steeper angle, it can't refract into the air. It undergoes total internal reflection. It obeys the law of reflection. The angle of incidence is the angle of reflection, and away it goes. So total internal reflection begins with ray 3. That's the dividing line between rays that refract into the air and rays that reflect. By the way, there is always a little bit of reflection even for these other rays. That reflection gets bigger and bigger, and by the time we get to ray 3, it becomes all that happens to the light going through there. So let's try to figure out how that happens. And here's what we've just recognized. At ray 3, at the critical angle, ray 3 is at the critical angle. That's this angle right here, and we want to know what that angle is. At ray 3, theta 2, the angle in the second medium, in air in this case, is 90 degrees. So theta 2 is 90 degrees. The sine of 90 degrees is 1. Sine theta 2 is 1. So in Snell's law, we have n1 sine theta 1, but I'm going to call theta 1 theta sub c because it's that critical angle, is equal to n2, the refractive index of the air. And so sine theta c is n2, the refractive index of the air, over n1, the refractive index of the glass. Let's do the numbers on that. n1 is glass, that's 1.5 approximately. n2 is air, that's refractive index approximately 1. The speed of light in air is almost as much as it is in vacuum. And so we work it out. Sine of theta critical is 1 over 1.5. That's 0.67. So theta critical is the angle whose sine is 1.67. Sine to, as 0.67. Sine to the minus 1 of 0.67 is 42 degrees. And that's exactly what we saw in our experiment. As we approached 40 degrees, we still got a little bit of refraction, but then a little bit past 40 degrees, and we got that total internal reflection. So for glass, the critical angle for total internal reflection is about 42 degrees, and you can calculate that for any other substance you would like, water, diamond, whatever, and it's internal reflections in the diamond, for example, that are causing a lot of its sparkliness. So that's how total internal reflection works, and that's what the critical angle is for total internal reflection. Let's just go over to our demonstration setup again and look at one example where total internal reflection is put to good use. So what I have here is a setup in which I have basically a prism-shaped piece of glass, basically an equilateral right triangle, and I'm shining light in perpendicular to the first side of it, and that light is hitting this diagonal, which is at 45 degrees. And remember, we just figured for glass, the critical angle is 42 degrees, so it's hitting it bigger than the critical angle, and so it undergoes total internal reflection, and it comes right out the bottom. And this thing behaves like a perfect mirror. And in fact, that is often used where we want really good reflection. We will often use total internal reflection instead of simply a shiny coating. One place where this is used is in binoculars. If you own a pair of binoculars, you notice they got a kind of bumpiness. The part you look through isn't in exactly the same direction as the lens that the light comes in through. It takes a little jog, and it takes a little jog by reflecting through a pair of prisms, not shiny mirrors, but prisms that are set up like this, so total internal reflection occurs. So that's total internal reflection, and that's it being used for this particular kind of reflection, just used as a mirror. But it's not a mirror, it's glass with total internal reflection. Let me just show you a couple other examples of total internal reflection before we wrap up. Here's a picture of a whale, or anything else underwater. If you're underwater and you look up, if you look at too steep an angle, you get total internal reflection. So this whale is seeing some planes flying over it. They're the whale watching planes. They're watching the whale, but the whale's watching them. And it sees them. It sees the entire outside world in that cone demarked by these two rays. There's a squid off to its right, and it sees that squid at almost the same angle as that right-hand airplane because the squid's light rays are beyond the critical angle, and so they undergo total internal reflection. Another important example of total internal reflection is the rainbow. The rainbow occurs because total internal reflection is occurring in raindrops, and it happens that at an angle of about 42 degrees coming out, you get a concentration of rays. That's where there's a bright band in the sky at an angle of 42 degrees between the line from the sun to you and the line where you see the rainbow. And because the index of refraction varies slightly with wavelength, that is with color, you actually see the colors of the rainbow. So the rainbow is another example. And let me end with one final example. Optical fibers, which have replaced copper wires in high-speed communication systems, are simply pieces of thin glass in which light travels down the glass by total internal reflection off the walls of the fiber. And the picture shows a bundle of a few optical fibers that can carry as much information as that huge, thick cable. And let me do a very quick demonstration of how that might work. Here I have a single strand of coaxial cable. It has a shielded conductor, some insulation, and an inner conductor. Here, much finer and able to carry much more information, is a single optical fiber. And if you'd like to see this optical fiber in operation, let me simply hold the optical fiber up to my laser. let the light head down the fiber, twisting around in all kinds of circles. That light will go in there, it will go round and round, and there it is. You can just see it coming out and shining on the screen, a little spot, as that light has gone all through that fiber and come out. So these fibers can carry enormous amounts of information because of the very high frequency of visible light. Okay, well, let's wrap up. We've seen that reflection occurs when light encounters an interface between two media. We've seen it can be complete or partial. We've seen that the angles of incidence and reflection are equal. We've seen that refraction occurs at interfaces of transparent media. It obeys Snell's law. N1 sine theta 1 equals N2 sine theta 2. And we've seen the phenomenon of total internal reflection and a number of its applications. Well, we could stop there, but if you're interested, here's a challenge for you. Here's that diagram about the clean CD. I'd like you to find the laser beam D at that layer at the top where the information is actually stored on the disk. So think about that a little bit, and I'll give you the solution. Here comes the solution. By Snell's law, sine theta 2 is sine theta 1 over n. By trigonometry, that distance x you see is t, the thickness of the layer, times the tangent of theta 2. D, what we're looking for, the diameter of that spot, is the big D, the diameter of the spot coming in, minus twice that x. Let's work through the numbers. You can do arithmetic, and you can make your calculator take trig functions, and the answer is 1.8 micrometers, 1.8 millionths of a meter, and that's why the CD is so immune from dust, because refraction gives it a very, very tiny spot size at the layer where it's reading the information.